Okay, so we were talking about semaphores, and we have said that semaphore is a variable, shared variable, that can be shared by many processes, and we can initialize it, and also we can perform two operations on that, wait and signal, okay? That is all we can do. And we can use them to synchronize our processes so that only one process, for example, can be in the critical region, and we can also use them for some other purposes that we will see, okay? So we said that we can perform two operations, wait and signal. Let's look what those operations will do, okay, when we execute them. So we can, in our application, we can define a semaphore, initialize it, and perform two operations in our programs, wait or signal, okay? Wait and signal. So what are those operations doing? So if we invoke wait, for example, on a semaphore. So when our application or program calls wait operation on a semaphore as, okay, assume we have created a semaphore variable that is shared between processes. When we call wait as, this is what is done, okay? If s is positive, okay, then the value of the s is decremented by 1 and wait returns. So wait just looks to the value of the semaphore as. If it is positive, that means 1, 2 or something, not 0, not negative, okay? If it is positive, then it just decrements the value by 1 and returns, okay? This is what wait is doing, okay, when you call it on a semaphore s. If, however, s is not positive when you call wait, okay, if s is not positive, then what is wait doing? So wait is checking the value of the semaphore, right? So if s is not positive, then what wait is doing is this. It just puts the calling process into sleep. Okay? It blocks the calling process. Okay? So wait is a system call. When the program calls the wait, okay, wait is executed, and when it is executing, it is doing this. It looks to the value of s. If it is positive, then it decrements s by 1 and returns. Then the calling application continues with the statement after wait, okay? However, if s is not positive, then the calling process is blocked by the wait system call. Okay, wait is executing and finds that s is not positive, then the calling process that calls wait now will be put into blocking mode, sleeping, waiting mode by the kernel, all right? So then the process will not be able to return from wait. It is blocked, it sleeps now, okay? The process has called wait and it is sleeping if s was not positive. This is what wait is doing. Whenever your program calls the wait system call, this is what's happening. If the value of the semaphore at that time is greater than 0, a positive value, then wait returns immediately. So your application, your program is not blocked. However, if wait was not positive, then, semaphore was not positive, then the wait system call puts your process into blocking mode, okay? You get blocked at that point in your program. You cannot be able to return from the wait at the moment, okay? You are blocked. This is what's happening when the semaphore value is not positive, okay? So how long you blocked? You are blocked until somebody does a signal operation on the semaphore, okay? And you are selected to be waken up. There can be some other processes that call the wait system call on the same semaphore and also get blocked if the semaphore value is not positive. This is possible, okay? So let's look to the other operation. What happens if a process calls the signal operation on a semaphore value, on a semaphore s? So if a process invokes the signal operation on a semaphore, then this is what is done inside the kernel as part of the signal implementation. So the signal is doing this. If there is one or more processes now sleeping on s, then one of them is selected and waken up, put into the ready queue so that it can be scheduled to run in the CPU whenever CPU schedule decides to run. And the signal system call returns. If, however, there is no process sleeping at that time, then s is simply incremented by 1 and the system call again returns, the signal returns, okay? So this is what's happening when your application calls signal on a semaphore variable s. Signal is a system call, it gets executed and is doing this. It looks to the value of s. If not the value of s, it looks to the whether there is a process waiting on s, okay? If there is at least one process, then it wakes that process up. If there are several processes, then it selects one of them, maybe the first one in the queue, and it wakes that process up. It puts it into ready queue, okay? It changes its mode from waiting to ready, so that that process can start running whenever the scheduler decides, and then signal returns. Or, if there is no process sleeping on that semaphore, that means there is no process that did a wait operation and blocked. There may be some other processes that did a wait operation, but they might have seen the semaphore value as positive and did not block, okay? So if there is no process that is blocking now on the semaphore because they did a wait operation on a semaphore which is non-positive, okay? If there is no such process, then S is simply incremented by the system call signal, and signal call returns, okay? This is what is done by the signal operation on a semaphore, okay? So keep in mind, these are the semantics of wait and signal, okay? So now we can use those operations, the semaphore, to implement some synchronization solutions. We can have two types of semaphores, binary semaphores and counting semaphores. A binary semaphore can be initialized to either 0 or 1. That's why it's binary. But a counting semaphore can be initialized to any value, any integer value, like 32, 48, 50, and so on, okay? So therefore, the integer value represented by the semaphore can change over an unrestricted range, okay, for the counting semaphores. But for binary semaphores, the value can be simply 0 or 1, okay? So a binary semaphore can be initialized to at most 1, and such semaphores are also referred to as mutex locks, mutual exclusion locks. That means they can be used to provide mutual exclusion. In other words, they can be used to solve the critical section problem, which requires mutual exclusion. So binary semaphores provides mutual exclusion, can be used for critical section problem. The counting semaphores, on the other hand, can be used for some other synchronization purposes, like, for example, for resource allocation. If, for example, you have several instances of a resource, let's say 10 instances, then you can use a semaphore to protect that, to be used for resource allocation, so that you can initialize such a semaphore to 10, for example, to represent the number of instances of that resource, okay? So we will see how we can use that for other purposes. So let's focus on the usage of the semaphores. So briefly we introduced the semaphores. That's just an integer variable that can be shared, plus it has an associated queue of waiting processes that might be sleeping on the semaphore. And it has two operations that an application can use, wait and signal, okay? So let's look to the usage of the binary semaphores, mutex variables that we have said, okay? So we have said that they can be used to solve critical section problem. Let's see how we can solve that problem, critical section problem, using semaphores. For that, we define a semaphore variable. Let's say it's mutex variable, okay, called mutex variable. And it will be shared by, let's say, n processes. There are n processes that would like to enter the critical section that is touching to the same shared data, for example, a file. And that semaphore has to be initialized to 1. Okay, you define a semaphore mutex and you initialize it to 1. Okay. So then each process is structured in this manner. So it has a critical section, a remainder section. It can go through them several times inside a while loop. Okay. From time to time, it wants to execute the critical section, and then in some other times, it will try to execute the remainder section, want to execute the remainder section. And now, we will just use these two function calls to implement our solution, synchronization solution, to ensure that only one process is in the critical region. What are those calls? We just call the wait operation on the semaphore mutex before the critical region, and then after the critical region, we just call the signal operation on the semaphore mutex. So now, the application programmer's job is quite easy. It just calls wait and then signal, and you are guaranteed that only one process will be in the critical section, okay? Let's see whether it will be really the case. So assume we have two processes, process 0 and process 1, okay? So they execute similar code, critical sections, remainder sections, and so each one is doing a wait operation on the semaphore before the critical section, and then after the critical section, each one is doing a signal operation on the semaphore mutex, which is shared variable, okay? It can be, for example, a kernel variable, that is created by one of the processes and shared by several processes, here in this case 2 processes. Okay? So the kernel implements 2 system calls, wait and signal, for which we have defined the semantics, right? We have already discussed what they are doing on the semaphore, or when they are called. Okay? So let's look, for example, what will happen if one of those processes starts executing, okay, and trying to do a wait operation on a semaphore. Assume those processes are started up concurrently, they are running, and one of them will be the first one to execute a wait operation. So the semaphore is initialized to 1, okay? Let's assume initially the semaphore mutex has a value 1, okay? So by the way, I should say that the wait and signal operations are atomic, meaning that the kernel ensures that when a process is executing the signal, the other process cannot execute the signal at the same time, but it can execute the signal when this process has finished executing the signal. All right? Similarly, when a process is executing the wait, okay, the other process can execute the wait operation if that process has finished executing the wait or that process has been blocked on the wait. Okay? In one of those 2 cases. So if a process is executing a wait, sometimes the wait may cause that process to block. After that block operation, after that process is blocked, another process can execute the wait. But sometimes, for example, the process may call the wait, but may return from the wait immediately when the semaphore value is positive. Then it will not be blocked. So while, for example, the wait is executed by one process, wait system call is executed, kernel code is running, okay? During this time, the kernel guarantees that another process cannot execute the wait system call, okay? For example, it may just disable the interrupt so that no context switch will occur, okay, during the wait execution in the CPU, and then it will enable the interrupts, and then context switch may occur, and then another process can execute the wait operation, okay? So this is ensured. Waits and signals are atomic. So when a process executes the wait, another process cannot execute the wait unless the process finishes with wait, returns from wait, or the process blocks. When that process blocks inside wait, then it will not be able to return wait, but at the time, again, another process can start executing the wait, okay? Because that process is now in the blocking state. The CPU can be given to somebody else, and that somebody else can execute the wait operation on the semaphore, okay? So now what will happen now? So assume that one of the processes will be the first one to execute the wait operation. Let's say process 0. So it will execute wait operation on the mutex semaphore. So it will see the semaphore value as what? 0 or 1? The semaphore value is initially 0 or 1? 1, right? So that wait operation will be executed on a semaphore that has value 1. So what will happen now? Do you think that process will be able to return from wait immediately or will be blocked? Let's look to the definition of the wait. So the implementer of the wait should ensure that wait is doing this. It looks to the value of s. If s is positive, then s is decremented simply by 1 and wait returns. Otherwise, if f is not positive, then no decrement operation happens, and that process, calling process, is put into wait, into blocking mode, okay? Is blocked, waited, okay? So here, in this example, initially, if this process calls wait on a mutex that has a value 1, what will happen? Do you think it will block or not? Not block, right? So the value of the semaphore will be what? Decremented? Yes, it will be decremented to 0, and wait will return immediately, so that the process will continue executing. It will not be blocked. So it will now be able to enter and execute the critical section code, right? So this process can be in the critical section code now. Assume it is executing in critical section code. So now, what will happen? Since this process is now returned from wait, another process can safely call wait, right? It's possible. Let's say that scheduler kernel decided to suspend that process for a while, so in the critical region, and has run another process, this one now. Assume this process now would like to execute the wait operation on the semaphore mutex now. What would happen? So what is the mutex value at the moment? 0, right? So the kernel variable has, mutex has 0. You execute a system called wait. So the kernel code wait is running now. It's checking the value of the mutex. What is that? 0, a non-positive value. So what will happen? The kernel puts that process to sleep mode. The kernel will not return from wait, but will just block that process. So that process now is blocked at that system call, okay? So basically the kernel just have a linked list of processes here waiting on that semaphore. So it is just adding that process to that linked list, okay? This is what is done by the kernel to block that process and to perform the wait operation, okay? So that process is now blocked. It cannot continue running, okay? It is blocked at that point without being able to return from the wait system call. Is it clear? So then how long will it take? So what will happen? As long as this process is in the critical section, that process will be sleeping, right? So here that means we are not wasting any more time if we cannot go into the critical section. In the busy waiting solution, we were just looping around, but here we are just put to sleep mode, okay? So that process is no longer schedulable by the kernel and cannot waste CPU cycles. Until that process finishes the critical section, sooner or later that process will run, execute in the CPU and finish its critical region. Then it will do what? It will perform a signal operation on the mutex, right? So what is that? That means it's calling a signal system call. It is now executing in the CPU. It will do what? It will check the list of processes that could be possible waiting on the semaphore. Is there a process in this particular example? Yes, there is a process. Now what is the kernel doing? The system signal implementation is doing. It is just changing the state of the process from waiting to ready, and it adds that process, removes from this list and adds it to the ready queue. So that process now becomes schedulable. And then signal is doing what? Returning. So then signal returns, so the application can continue here depending on the kernel scheduler. Now at this point, this process is schedulable and that process is schedulable also, so the kernel can continue to switch to that process or can decide continue running this process, okay? Both of them can happen. We don't make any assumption about that. So this process can run in the remainder section or the kernel can decide to run that process. If the kernel decides to run that process, from where it will continue? From this point. So because now this wait will return, okay? Wait system call will return. The process will no longer be in the blocked state, okay? The kernel, the system, the process is put into the ready queue and the process will continue running whenever it is given the chance of using the CPU from that point, okay? So that means it has returned from the wait and it will be able now enter into the critical region. Is it okay? Yes, it's okay because the other process has left the critical region, all right? Is it clear? So in this way, only one process is ensured to be in the critical region. Any questions here? This is how we can utilize the semaphores actually to use the to solve the critical region problem, to provide mutual exclusion. Here we are using binary semaphores. You are using a semaphore that is initialized to 1. Is it clear? And for the application programmer, it is very easy actually. You just call a function and then another function. You just declare a variable, semaphore variable mutex that is created inside the kernel, okay? Initialize it to 1, and then we are not showing that here, but assume you will exercise with that in the projects. You will see how we can use, for example, how we can create a semaphore and access it using these operations and so on, okay? Utilize, for example, that semaphore to protect your critical regions with the project. You will exercise with that. So you just create a semaphore and use those operations to protect your critical regions. And you are ensured that if there are several processes that would like to enter the critical region, only one of them will be allowed to be in the critical region at a time. Any questions here? Yes?
Does the signal wake a process from the sleeping to randomly? Or?
Yes, you can think it can be randomly. It depends actually on kernel implementation. It can be first come, first served based, okay? The first process that is added to the queue will be removed from the queue earlier. Otherwise, if you, for example, remove the last process that added, then we can have some starvation problems, okay? So usually it can be simply a first in, first out queue. In this way, it can be, for example, not cause starvation, all right? Okay, any other questions here? All right. So if there would be some other processes, if one process is in the critical region, while it is in the critical region, what is the mutex value? 0. So assume this process is run, it does a wait on the semaphore, what will happen? That process will be locked. Assume we have another process, process 2, that does a wait on the semaphore to enter the critical region. What would happen to that process? It will also be blocked. It will not be returning from the wait. Another process can call the wait, right? Because that's blocked. And it will be also blocked. So there can be actually several processes that are blocked on the semaphore. That means they are added to the waiting queue associated with the semaphore. Okay? They will be there until the process leaves the critical region and does a signal operation. And then at that time, the signal system call will wake them up. One of them will wake one of them up, and that process can be in the critical region. When that returns or finishes the critical region, that will do a signal operation. And that signal operation again will select one of the remaining processes in the waiting queue and will wake that process up. Okay? In this manner, we are, the other process will be able to have a chance to enter the critical region. Is it clear? All right. So this is how we can use the semaphores for mutual exclusion. So what was the others use? So this is not the only way or on the problem that we can use the semaphores. We can use the semaphores for some other synchronization problems as well. So it's a powerful tool. So what is another problem? So remember, we have said this. We have said that we did not learn a mechanism that will enforce a process to go to sleep until an event happens. So far, you don't know such a mechanism. If you want to do that in your programs, you were declaring a variable maybe, right? And checking that variable value in a while loop, whether it is set to false or true. It can be, for example, set to true whenever an event occurs, and then you can go ahead and do something and understand that that event has occurred. So you can enforce your process to wait until an event has occurred by just busy looping on a variable, Boolean variable, right? This is what you can do. But actually, it is desirable to enforce a process to go to sleep instead of busy waiting until some event has occurred. So now this is such a mechanism now. Semaphore is a mechanism or primitive that a tool that you also can use for this purpose. You can use that semaphore, the semaphores for this purpose as well. Okay, let's see an example, for example. Okay, so assume we have two processes, all right, that will be run concurrently. Okay, so you cannot make any assumption during which time a process is running and during which other time a process is running, right? So from time to time, this process will run. From time to time, that process will run, depending on the current scheduler. You cannot any assumption, but they will be running concurrently in the system, right? In a pseudo-parallel manner, sharing the same CPU, memory, and so on. This is guaranteed, but you don't know when a process will be run and when the other process will be run, okay? But assume you want this. You want this process. Okay, assume this process has a statement S1 and that process P1 has a statement S2, okay? Assume you want that S2 to be always executed after S1 is executed. This is the thing that you want, assume, okay? How can you enforce? For example, assume the scheduler has decided to run this process, so it will be running the CPU in the CPU and S2 will be executed, but it's not you want. You want S2 to be executed if S1 is executed. What you can do, you can maybe do a while loop here, check a condition variable, maybe a flag, which will be only set whenever this is executed at this point, okay? Then it is set, then you will be able to break out of the while loop and execute S2. This is a possible solution, but it causes this to busy wait, okay? So you don't want that. You want that to sleep. For example, it will start earlier. If it's about to execute S2, you don't want that process to execute S2. You want to enforce that into sleep, okay, until P0 execute S1. After that, you want to allow that process to continue, okay? Assume this is what you want to do. Assume we definitely want to have S1 executed before S2. Then how can you solve this problem? Using a semaphore. Yes? Yes, exactly. So this is the exact solution actually. But so you define a semaphore, right? And what should be the initial value of that semaphore?
0.
0, right? So it's important. So now this is the solution as you have described. So here we define a process, a semaphore, sorry, X, that's initialized to 0, okay? So then you can program your programs in this way. Before S2 here in this program, you have to be calling wait operation on semaphore X, and in this program, after S1 statement, you call the signal operation on semaphore X, okay? So semaphore is created by one of those processes, initialized to 0, and is shared by those processes. Remember the project 1, you have a message queue that has a name. Using that name, actually, you can refer to the same message queue created inside the kernel by several processes. Each process is using the same name to refer to the same message queue. Similar idea is implemented with the semaphores, actually. You can identify the semaphores, you will exercise with those, with a name one of them may create and assign a name to a semaphore, one of the processes, okay? And the other processes may use the same name, okay, to refer to the same semaphore, okay? In this way, they will operate on the same semaphore. So assume we have created such a semaphore X by one of those processes, and now what will happen? So one of these processes will be run. Assume this process is run earlier and is come to this point, okay? So it will do a wait operation on the semaphore which has a value X, semaphore X which has a value 0 now. So what will happen to that process? It will be blocked because the semaphore has a value 0. So it will be blocked until when? Until the other process runs, executes S1 statement and does a signal operation on the semaphore. So that signal operation will cause that process to be now, again, unblocked and be able to run whenever the schedule decides to run, okay? So then that process will be able to continue at that point. So it will execute S2 afterwards, after returning from wait, okay? After it is unblocked again, it will execute S2. Now, if we come to this point now, that means we are sure that S1 is executed, right? So in this way, you solve this synchronization problem. So this was a synchronization problem. You want process P1 wait until P0 execute S1, all right? This is a synchronization problem, and you can solve it using semaphores. You can have various other synchronization problems that can be solved using semaphores. You can use more than one semaphore. You can initialize them to not 0 to something else, and so on. So you can use these semaphores to solve some other synchronization problems as well, like, for example, resource allocation problems. Assume we have several processes and processes that would like to use a resource, okay, that has 5 instances. So if a process would like to take a resource, okay, if there is an instance available, it will go ahead and use. If there is no instance available, it will wait until an instance is available. Then you can just declare a single semaphore initialized to 5. Every process that would like to use the resource will do a down operation, wait operation on the semaphore. If you have some instance available, that means the semaphore will have a positive value. The wait will return immediately, but the value will be decremented. That means now the available resource is decreasing, and when it becomes 0, that means all the 5 instances are used by 5 different processes. Then what will happen? The next process that does a wait operation on the semaphore will find the value of the semaphore as 0, and it will be blocked because there is no instance of a resource available. So what will happen then? It will wait there, it will be blocked until one of the processes that has a resource finishes with that resource and does a signal operation on the respective semaphore. Then that waiting process will be unblocked and will be able to use the resource, okay? So for resource allocation purposes, you can use also the semaphores. And you can initialize, define an associated semaphore and initialize it to the number of instances, for example, of that resource. So for that purpose, you can use the counting semaphore, for example, okay? So here, for example, we use a counting semaphore for a similar purpose, like resource allocation, but the purpose here is actually to enforce a consumer, okay, to enforce a consumer to sleep if there is no item available in the buffer. Remember the producer-consumer problem? Producer was producing items and consumer was removing items from the buffer. And if the buffer has no items available, okay, what do we do as the consumer? As the consumer, we have to wait until there is at least one item in the buffer. Previously, we were just looking to the count value and so on, busy looping, right? Now we can do something else. As the consumer now, we can do this. We can define a semaphore full cells, okay, a semaphore full cells, which represents the number of items in the buffer. In other words, the number of slots that are full in the buffer. Assume buffer has at most buff size elements or slots initially all empty. So that means there is no full cell or full slot at the moment. So therefore we initialize the full cells, the number of slots in the buffer that are full. Initially it is 0, okay? So whenever, for example, the producer puts an item, it will increment this semaphore by doing which operation? Signal operation, right? So whenever the producer puts an item, it will put it into the buffer and it will increment the full cells semaphore by doing a signal operation. So now what we can do as the consumer, we can just do a wait operation first on the full cells and then continue trying to remove an item. So if there is no full cells available, that means if there is no full slot in the buffer, that means there is no item in the buffer, this call here will cause that consumer to sleep. Sleep until when? Until producer produces an item and puts it into buffer and then does a signal operation. So this is what we want, right? We want the producer, the consumer to sleep, not busy wait, until an event occurs. Here the event is the buffer has at least one item. That event will happen after the producer puts an item into the buffer and does a signal operation, signals that event in this way, okay? Does a signal operation on the respective semaphore. In this case, the consumer will be waken up, right? And will be able to continue. Here it can remove the item from the buffer and consume the item from the buffer, okay? So, for example, at that time, a context switch may happen, producer may run, and insert many items into the buffer before the consumer run again. So, full cells, for example, may become 7. That means 7 items are available in the buffer. So then let's assume consumer is run. Assume it was in this point, so it loops around and does a wait operation on the full cells semaphore. What will happen now? Do you think it will be blocked again? So the full cells value is now assume 7. There are 7 items in the buffer. Do you think it should block? No, it can retrieve an item because there is an item available, right? At least an item available. So what should happen now? So what does wait operation is doing? If the full cells is positive, it is not causing the calling process to block. It is just immediately returning after decrementing the full cells by 1, right? This is what the wait operation is doing of a semaphore. It is defined in this way. So then full cells will be decremented by 1. It will become 6, so it will return immediately so that the consumer can go ahead and remove one item without any problem. There is an item, and then consume that. So there are now 6 items in the buffer. So full cells semaphore represents the items available in the buffer. In this case, for example, you can enforce its value to be maximum buffer size, okay? Since there are buffer size slots available in the buffer, the full cells should be having a value at most buffer size. So now we again use semaphores, a semaphore here, for a different synchronization problem, to enforce the consumer to sleep as long as there is no item in the buffer. This is a different synchronization problem, okay, than the critical section problem. Is it clear? So you can use the semaphores for various purposes. So this is also a synchronization problem, as I said, consumer-producer. So the consumer and producer is synchronized in this manner. So what will happen? For example, if you look to the full cells here, okay, initially the full cells is 0, right? Then the producer can produce some items, the consumer can retrieve them, and producer runs and puts some more items, and consumer retrieves them. And if there is no item here, then what will happen to the consumer? It will just block, okay? And then the producer can produce more items. At that time, the consumer can run and remove items. Producer can put some more items, at most buff size items, into the buffer, and so on. So this is the synchronization requirement here. We want the consumer to be after the producer, but the producer cannot be too much ahead of the consumer as well. It cannot produce more than buff size elements and put them into the buffer, okay? This is a synchronization problem that requires that as well. So basically, if we look to the items that are produced and that are consumed over time, the difference between them can be at most buff size. And the consumer can never cross the producer curve here, okay? So this is a synchronization requirement, and we can implement that using the semaphores, okay? So this synchronization requirement can be implemented and can be solved using the semaphores. All right, any questions so far? We will see actually how we actually implement the full implementation of the producer-consumer problem. We will see that how we can do that with the semaphores later on, okay? I just showed you one portion of that. This is not the complete solution here, okay? This is not complete solution. This does not cause the producer to wait if the buffer is full, okay? For that, I have to define another semaphore. We will see that later on. Any questions here? So let's look how we can implement the semaphores actually. How we can implement the semaphores. We have to guarantee that no two processes execute wait and signal system calls at the same time. So actually this has to be enforced by the kernel, okay? And the kernel can do that, for example, by actually disabling the interrupts in the implementation of the wait and signal, those procedures while implemented in the kernel. In the beginning, the kernel can just disable the interrupts while it's implementing or it is running the wait system call or signal system call. So now let's look how we can implement. In the kernel, we can use such a structure, for example, to represent a semaphore. So a semaphore has a field, an integer value, plus a linked list of processes that may be possibly waiting on the semaphore, initially empty, okay? So this may be the semaphore structure defined inside the kernel. Whenever you create a semaphore, an instance of that structure will be created, and the semaphore may be initialized to some value, and the linked of processes that are waiting on the semaphore will be empty initially, right? So then, what are we going to do? With each semaphore, we have an associated waiting queue, this list, okay? And each entry in a waiting queue has two data items, all right? A value of type integer, a pointer to the next record in the list, okay? So now, we will use two operations, block and wake up. These operations will be used by the kernel. Whenever it needs to block a process, it will call such an operation to cause that process to block. And whenever, for example, during the implementation of the signal, whenever it would like to wake up a process, it will call such a kernel function to wake that process up. Assume these are available by the kernel. Block and wake up procedures are available. Block places the process invoking the operation on the appropriate waiting queue. Okay, it changes the state of the process from running to waiting. And wake up will remove one process in the waiting queue associated with the semaphore and place it into the ready queue, okay? Assume those operations are available by the kernel. Again, this has to be implemented by the kernel implementer, right? So now, this is how we can implement the semaphores. The wait and signal. So, wait system call can be implemented inside the kernel like this, okay? This is the kernel code, assume, okay? So what is it doing? It is first decrementing the semaphore value by 1, okay? And then it is checking the value. If it has become less than 0, okay, that means its value was not positive. So then what we should do? The kernel has to put that process, calling this, into the waiting queue associated with the semaphore. So this process is added to the waiting queue, S list, okay? List is associated with the semaphore as, it is the waiting queue associated with the semaphore, okay? And so that process is added to the waiting queue and the process is blocked. Its state is changed to what? To waiting. It was running in the CPU before calling this system call. It is taken out of the CPU and so on, okay? So this is what's happening with the block. So when block returns later on, which can happen whenever another signal, for example, signals, okay? When that process unblocks, it will continue executing from here, which means that it will immediately return from the wait because there is nothing else in the wait system call to execute anymore, okay? So next time the process is unblocked by a signal, okay, it will continue its execution from this point in time, from this point in its code, okay, in the kernel. So that means it will return immediately from the wait and will execute some other statement after the wait in the program. Is it clear? So then let's look to the signal operation, how we can implement it inside the kernel. So the kernel implementer implements it in this way. So signal system call, signal on a semaphore S. What are we doing here? So we first increment the value of the semaphore by 1, okay? So if value is now still not positive, okay, still not positive, okay, then that means there was a process waiting, okay? So we remove one process from the associated waiting queue of the semaphore, let's say process P, and we wake that process up, meaning that we change its state from waiting to ready, add it to ready queue, and make it ready to execute, okay? It's up to the kernel scheduler when to execute that, but it is now ready to execute, okay? This is what's happening with the signal. And then signal returns. This is the implementation. The kernel implementation should look something similar to that. Of course, this is a simplified way, okay? We don't show how the disabling of the interrupts here, okay? We don't show it. If you do not disable the interrupts, if a process calls the signal here, that process may run for a while inside the kernel, and at that point, a context switch may occur if it's a preemptive kernel. Another process can run the signal system call again and may access the same shared data. This is something that we don't want to happen. Therefore, you may want to disable the interrupts at this point in order to not context switch to a different process until you execute the signal system call, so that you are touching to this shared value without any problem and so on, okay? And then you, at this point, you should enable the interrupts again, okay? Here, you should disable the interrupt here and enable the interrupt here, okay? Or here, after putting the process into blocking mode. So, if I ask you this question, do you think the signal can block the process? No, right? So signal is a system call that never blocks the caller, okay? It just does these operations and it immediately returns. But about the wait system call, the caller may be blocked, right? From time to time. And one more thing that I would like to ask to you is this. So here the semaphore value actually can become negative. Okay? A process may do a wait and can get blocked. May do a wait, can get blocked. Another process may do a wait and can get blocked, and so on. Assume we have a process now in the critical region. All right? So here there may be several processes, they do a wait, and each time they do a wait, the semaphore value gets negative, 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 and so on, okay? So actually the absolute value of that negative value is the number of processes that are waiting. Okay? If you just look a little bit more to the code closely, and if you analyze it, you will see that this value here represents, if it is negative, the number of processes that are sleeping on the semaphore. If its value is 0, okay, then that means there is no process sleeping. Here, for example, when you perform a signal operation, you first increment it, okay, by 1. So after you increment it, if it is 0, that means it was -1. That means that there was one process sleeping. Or after you increment it, if it is still negative, that means there were some other process. If, however, after incrementing that, if it is 1 or greater than that, that means the S value is not smaller or less than 0. That means there is no process waiting, okay? So that means you are not going here to wake up a process. You just return immediately. So you increment the value. If it is after incrementation is 1, that means the value was 0. So there is actually, there was no process sleeping if the value was 0, okay? Because absolute value of 0 is 0, right? If, however, the value was -1, after incrementation, it will be 0, so you will enter here. If the value was -1, that means there was one process that is sleeping. Then you will wake that process up. Okay? Is it clear how we can implement the semaphores inside the kernel? Of course, this is a simplified pseudocode. It's not showing the disabling of interrupts and so on. Okay, we can stop here and we will continue next time.